If any of you wants to volunteer, you're more than welcome to record it and get better angles. If not, just deal with the shitty angles. Good thing is we got good notes, so theoretically that'll do the trick. I gotta be careful not to cuss in front of the camera. All right. So we're going to be moving really quickly. I apologize ahead of time for that, but it's a short course. Got a lot of stuff we need to discuss. Got a couple things to wrap up on material for Exam 2, and then we're going to stop and we're going to start moving into Exam 3 material. We've already covered the bulk of Exam 2 material. I hope you guys are getting your homework done. I'm hoping you're finding it doable. We'll have more practice on Thursday in lecture on Exam 2 material, but yeah, today we're going to move ahead to Exam 3 stuff after we cover one last bit of business. We've been looking a lot at ionic solubility. The things that we discussed regarding ionic solubility. Sorry, let me find the Zoom. The things that we discussed regarding ionic solubility are going to be factors in all solubility problems. If you ever take a thermodynamics course, they'll talk to you about the entropy of mixing. When you have two distinct, we're going to call them phases, but substances. You know, one's composed of one kind of a molecule and the other one's composed of another kind of a molecule. There's more disorder if those molecules are mixed together and spread out. There's just more ways to achieve this state where all of the molecules are mixed in the solution than there are ways to achieve this state where one half of the solution contains one molecule type and the other half contains the other. So there's always kind of this natural tendency for substances to make solutions of one type or another. Entropic, there's an entropic tendency. But also a factor are those electronic forces in each system or in each phase. So there's certain forces that A and A molecules exert on one another, and those forces act to bind them together. There's certain forces that B and B molecules exert on one another, and those forces act to bind B molecules together. There's a different kind of force that binds B molecules to A molecules. The forces are a function of the nature of the charges and the charge separations in the molecules. And so when we go from one kind of separated state into a mixed state, we're always concerned with the competition between the forces here, or the relative strengths of the forces in one state versus the strengths of the forces in the other. And if the strengths of the forces in, for solubility problems, if the strengths of the forces in the kind of separated phases are much, much stronger than the strengths of the forces in the mixed phases, then the separated phases will be highly favored thermodynamically. It's your delta H in that delta G equation that is the function of the electrostatic forces in the phases and the states of matter. So you're always, the question is always about relative strengths of binding interactions between the two phases. We covered that. Just want to go back to this diagram. If a thermodynamics instructor sees these diagrams, they'll probably chew me out for not giving you the entire story, but I think these are good useful learning tools, and so I'm going to use them anyway. At the end of your ionic solubility discussion, I put little bar graphs like this to demonstrate the different kinds of situations that something is going to be insoluble or soluble in endothermic or soluble in exothermic. We introduced these in the context of solubility of ionic substances. in the insoluble case, the strengths of the forces in the separated phases, so when it was salts, we were talking about the strengths of the forces in the crystalline lattice structure of the salt, and I guess it would be the strengths of the forces in the water, are they're so strong that they overpower the strengths of the forces in the dissolved state and the entropic tendency to dissolve. So if you've got really, really, really powerful kind of electronic interactions in the separated phases, they'll be dominant and you won't have solubility. The two substances won't mix. We also have the case, you can have the case where the strengths of the forces in the separated phases are actually stronger than the strengths of the forces in the dissolved phases, but because of that contribution from entropy, you have just enough driving force to get it to go, even though the dispersed phase or the separated phases forces are stronger. And so in that case, you're going from stronger forces to weaker forces, and you'd have to go up in electrical potential energy. That's a positive delta H. You would have an endothermic reaction. Last case, you've got stronger net forces in the solvated kind of mixed phases than you have in the separated phases. And you have that entropy term that favors the mixing of the substances. Well, in that case, you're moving from weaker forces to stronger forces, so you actually go down in electrical potential energy, and energy is released. You've got an exothermic reaction, and it's soluble. So we went over those three different kinds of cases. Now really, that's pretty much the thermodynamic argument. Now all we really have left to do is to kind of consider what different kinds or different types of forces we've got to be concerned with in these problems. So we talked about a little bit of these these forces before. I'm just going to go over them again. I'm not sure which one of these is the force that Luke used, but I'm pretty sure it's one of them. It makes me laugh, and that's all that really matters to me. I hope you laugh along, but if you don't, I don't really care. Okay. Ion-ion forces. When you have absolutely charged particles, one particle is negative charge, one particle is positive charge, or you can have the same charges. But essentially in solids, like in the salts that we saw, it's those ion-ion forces that bind the salts together. Those forces are really important. It's the electrostatic interaction of a positively charged ion and a negatively charged ion. When those guys come together under the influence of those forces, it's an energy lowering thing. We saw that these kinds of forces exist in the solid phase. I'm not going to throw too much at you, but the truth is that to some degree, there are ion-ion forces in dissolved phases. If you take an aqueous solution and you dissolve a salt in it, I have a marker. Where did I put my markers? If you have an aqueous solution and you allow a salt to dissolve in it, the ions in the salt actually have energy-lowering interactions just based on the fact that they exert electric potentials on each other through the solution. It's actually energetically favorable on some level to have ions dissolved in solution. So you have ion-ion forces that exist between ions dissolved in solution, but because the R value here is really large, compared to the R value in the solid, these ion-ion forces are much stronger in the solid. Okay? Ion dipole forces. So these are the kinds of forces that are responsible for the solubility of salts in water. You take an ion, we've seen this a million times, you put it in a water solution, and water will rotate its dipoles towards the appropriate ions, right? If you've got a positively charged ion, water rotates its negative dipole towards that positive ion. And again, anytime you bring positive and negative charge close together, you've got a potential energy lowering interaction, right? So those ion dipole forces